Okay, so the proof is quite straightforward. We want to prove this statement is true. So if there's any elements that is in this set, which is the complementary set of the union of A and B, then it means that the element is not in the union of A and B. That is the definition, right? And this means that such element is not in set A and set B at the same time. That means the element should be in the complementary of set A, and at the same time it will be in the set of the complementary set of B as well. And that is the definitions of intersections. Okay, so we complete the proof here. And you can do it by yourself for the second part of these questions as well by yourself. And also you can add more subset into, for example, like now we want to know whether the ABC, the union of ABC holds like this one. Oh. B and C. Like this one. So you try it by yourself, okay? Right? And any questions before we move on? No? Right. And then is the order pairs and relations. So what is the order paired? Like if we have two sets, then we can define the order pairs in the following way, which the orders matter this time. Okay. So for example, AB. So for example, we have two sets. The set X contains the elements A and B here, and the set Y contains numbers 1, 2, 3. So we can define the order pairs in the following way. We just put it in the parentheses here, and put the first elements from X and put in the first tube here. And the second tube, we put the elements in Y's here. And that is the order pair. And notice that the orders matter. So XY doesn't equals to YX. So the easiest way to to think about it is the xy plane. Okay, so in the xy plane, you won't say that the point 1, 2 is the same as the point 2, 1, right? So these two are not equals. Okay, the only way, the only, how to say that, exceptions is when both numbers are the same. For example, like 1, 1 and 1, 1. So in this case, of course, they are the same, right? So that's why I put it here. So x, y not equals to yx if x and y are not equal, right? And this is the way we defined the odd order paired from 2 set, which is we use the symbols here. This is called Cartesian products. So you just list all the possible combinations here, and you can get, for example, like here, I put it z, right? Right, and the binary relation is a subset of x and y. For example, if I only want to pick this one, A3 and B2, so that will be a subset of such from such ordered pair set. So for example, I write it down. R contains A3 and B2. So in this case, R is a subset of X Cartesian products of Y. Write it this way. In our example. So that is the definition 5. Okay. Right. And there are also some common use set here, which I'm not going to talk about. Like, we're not going to talk the details of it. For example, like the natural numbers, which is the positive, I mean, like a positive integer. So starting from 1, 2, 3, 4, 5, 7, like 4, 5, 6, 7, continue to positive infinity. And a bigger set is integers, which contain the negative part of it, the negative part of the natural numbers, and also the 0 here. Oh, so there's a typo. Why do I? That's weird. Okay, so it is like negative 1, 2, 3, and positive 1, 2, 3. Sorry, there's a typo there, and I'm going to fix it later. So this part should be positive. Okay, sorry about it. Right, and then is the rational number. So you can write out any rational numbers in the fractions way. And the numerator will be 1 elements from the integers, and the denominator q should be the elements of natural numbers here. And also the greatest common divisors of p and q should be 1. Okay, so that is the definition of rational number. And an even bigger set is the real number, which contains the rational number and also irrational number, for example, like square root of 2. And also you can construct an n-dimensional real coordinate space, for example, like R2, which is our xy plane we often used. Okay, any questions? Right, good. So if there's no questions, we will have like 15 minutes break and see you back in 3:30.